Recycling a bus involves a multi-step process to recover valuable materials and minimize environmental impact. First, workers remove reusable components like the engine, transmission, and wiring. Hazardous fluids are drained safely. Next, industrial shredders such as the SSI 4200 crush the remaining structure, capable of processing 20 to 50 tons of material per hour. Magnetic separators extract steel, while eddy current systems separate non-ferrous metals like aluminum and copper. Plastics and rubber are sorted using optical and pneumatic systems. These recovered materials are sent to manufacturing plants for reuse. In the U.S., recycling contributes $116 billion to the economy, highlighting its environmental and economic significance. ArcelorMittal, the world's second-largest steel producer, manufactured 57.9 million tons of steel and 42.4 million tons of iron ore in 2024. The production begins with raw materials, iron ore, coke, and limestone, fed into blast furnaces operating at 2,200 degrees Celsius. The molten iron is transferred to basic oxygen furnaces, BOF, where oxygen is injected to reduce carbon content, producing liquid steel. The steel is cast continuously into slabs or billets, then hot rolled at 1,250 degrees Celsius to achieve desired thickness. Some coils undergo cold rolling for precision. Surface treatment processes include galvanizing and color coating for corrosion resistance. Factories integrate high levels of automation, yet skilled workers remain essential for monitoring, maintenance, and adjustments. In a move toward green steel, ArcelorMittal invested $120 million in Boston Metal's zero-carbon technology. This blend of innovation, automation, and sustainability allows to lead global steel production while minimizing environmental impact. Bremen Machinery's production process, featuring their new plate rolling mill from Hustler Walls, begins with the preparation of flat plates. These plates are intentionally oversized on both edges to allow precise edge welding during the rolling phase. After welding, the plates undergo a preheating process to ensure optimal malleability before being fed into the rolling mill. The advanced three-roll mill shapes the plates into large cylinders, with an external diameter reaching up to 2,076 millimeters. The welded seams are treated using underwelding to ensure strong, durable connections. Once rolled, the plates are bent using a powerful press with a capacity of 3,000 tons, which allows for precise shaping. An example of the mill's capabilities is the rolling of a 43-ton steel plate, showcasing its ability to produce large, high-quality components. This process combines advanced machinery and expert handling to create robust, large-diameter steel products. The wind tower manufacturing process involves robotic assembly lines, CNC machinery for precise component fabrication, automated testing systems, and quality control procedures to ensure optimal performance and durability. Interrupted turning involves rotating the workpiece while the cutting tool intermittently engages, utilizing CNC machinery for precision. The system monitors load variations in tool wear for consistent output. JG Automotive, a commercial office of the Befrangi Group in Spain, is a leading manufacturer specializing in the production of metal parts for various industries, with a particular focus on the automotive sector. The company leverages a sophisticated and diverse production process that combines several advanced technologies, such as forging, casting, machining, stamping, laser cutting, welding, and precision parts manufacturing. This comprehensive approach ensures that JG Automotive meets the high-quality standards demanded by its clients in the automotive, aerospace, and other industrial sectors. The production cycle begins with the selection of raw materials, which are then processed using forging or casting techniques. In forging, large presses apply high pressure to shape the metal into the desired form. Alternatively, casting involves melting metal and pouring it into molds to form components. Once the basic shape is achieved, parts undergo precision machining. Using advanced machinery, these components are finely adjusted to meet exact specifications, ensuring high accuracy and smooth finishes. Stamping and laser cutting are integral steps in creating more intricate and detailed components. Laser cutting, in particular, allows for precision cutting of metal parts with complex shapes, while stamping is used for larger-scale production of flat metal components. After shaping, welding is employed to join metal parts together, creating stronger, more reliable assemblies. For components that require intricate detailing, JG Automotive uses lost wax casting, a process that enables the production of parts with fine details and tight tolerances. Furthermore, the company's investment in toolmaking ensures the creation of durable molds that facilitate the efficient mass production of components. Once all the processes are complete, the parts are carefully inspected to meet strict quality standards. JG Automotive's commitment to precision and quality ensures that their parts meet the rigorous requirements of the automotive and other industries, helping to drive innovation and performance in every product they produce. The production process of SA240 involves cutting, forming, welding, solution annealing, quality inspection, and surface finishing for durability. The production of wire and cable at General Cable follows a highly systematic and detailed process that ensures the manufacturing of quality products suitable for various applications like energy, industrial, and communication markets. The process starts with the selection of conductors: copper, aluminum, or fiber optics. Copper and aluminum are the primary conductors used, and each is processed based on its application. Copper, extracted from the earth through mining, undergoes smelting and refining to create pure copper cathodes and rods. These rods are then used in wire and cable manufacturing, or further processed at certain General Cable plants. Aluminum is also extracted and refined before being drawn to the required gauge size. For fiber optic cables, the conductors are made from glass or silica. This transparent material transmits data with minimal electromagnetic interference and is used in specialized communication cables. Once the conductors are ready, they undergo the next step in the process, where they are drawn down or stranded to the appropriate diameter or gauge size. The conductors are then passed through an extruder, where they are coated with insulating materials like polyethylene or rubber. The insulating compounds come in pellet form and are fed into the extruder, where they are transformed into a pliable state using heat and pressure. The extrusion process is followed by curing in a continuous vulcanization (CV) process, where the rubber insulation is hardened under high pressure and heat. After insulation, the wires are passed through a cooling system to maintain their shape. As part of quality control, monitoring devices ensure both physical integrity and electrical characteristics are in line with standards. Operators are empowered to interrupt production at any time to correct any issues before the next process step. After the conductor is insulated, it may be twisted, braided, or bundled together with additional elements such as fillers or shields, depending on the specific product requirements. These additional features enhance the cable's mechanical strength, provide electrical shielding, or offer protection against environmental factors. For example, cables that require extra protection from external elements like moisture or physical damage may be shielded with metallic layers or coated with aluminum tape. The final step in production involves packaging the completed cables in boxes, on spools, or reels, and labeling them with critical product information, including agency approvals, traceability codes, and footage markings. The cables undergo rigorous testing, including dielectric strength and capacitance tests, to ensure compliance with industry standards. The production begins with the careful selection of raw materials. These materials are then melted in high-temperature furnaces, where precise control over temperature and composition is essential. Once the metal reaches the desired molten state, it is poured into molds to form billets, which serve as the foundation for the final forged products. After the billets are formed, they are subjected to a heating process, where they are preheated to an optimal temperature. This stage is crucial because it prepares the billets for the hot forging process, ensuring they are soft and malleable enough to be shaped under high pressure. The heart of the production process lies in the hot forging itself. Using heavy-duty forging machines and automated conveyor systems, the preheated billets are mechanically shaped into their final forms. The machines exert significant pressure to mold the billets into the precise dimensions and characteristics required for their intended use. FPM and Farmbrass specialize in providing full-stack metal hot forging solutions, focusing on the production of billets. The process of creating billets involves multiple steps that are meticulously carried out using advanced machinery and technology, ensuring both efficiency and product quality. Once the billets have been forged, they undergo a cooling phase. Depending on the specific requirements, additional heat treatments or mechanical processes such as quenching or tempering are applied to enhance the material's strength and durability. The billets are then inspected for quality, ensuring they meet industry standards before being shipped for further processing or use in various industries. Throughout this process, human oversight plays a vital role in monitoring the operations, while the machines and automated systems handle the bulk of the work, ensuring a high degree of precision and efficiency. This synergy between human expertise and technology enables FPM and Farmbrass to consistently produce high-quality forged billets. Pima is a world leader in welding automation, offering cutting-edge systems that are designed to optimize manufacturing processes across various industries, including shipbuilding, power generation, heavy equipment manufacturing, and more. The process begins with detailed planning and consultation, where PEMA's engineering team collaborates with clients to understand their specific production needs and identify the best automation solutions. At the core of the systems are robotic welding stations that work in tandem with welding positioners, columns, and booms. These pieces of equipment are engineered to precisely manipulate and position workpieces during the welding process. The robotic stations are programmed for high-speed welding, ensuring repeatable precision with minimal human intervention. This automation results in a significant reduction in production time while maintaining the highest standards of quality and consistency. The systems are highly adaptable, incorporating flexible assembly and welding stations that can handle parts of various sizes, shapes, and complexities. This versatility allows the system to cater to different stages of the production process, ensuring that the workflow remains continuous with minimal downtime. In addition to improving the efficiency of the welding process, PEMA's automation solutions are designed to boost overall productivity and optimize material use, leading to cost savings. In addition to the technical capabilities of their systems, the company offers full-service support, overseeing the entire project, from the initial consultation and system design to installation, commissioning, and operator training. The integration of these systems is smooth, with the providing continuous support throughout the transition to ensure the systems meet operational goals and maximize return on investment. Furthermore, the company's automated systems are equipped with advanced features such as automatic part loading and unloading, sophisticated welding control systems, and enhanced safety measures. These features not only improve the quality of the welds, but also ensure operator safety and prevent costly mistakes. The melting aluminum process begins with collecting aluminum cans and preparing the necessary equipment. A charcoal chimney is filled with briquettes, which are ignited using a torch or lighter fluid. A hairdryer is connected to an ABS pipe to supply additional airflow, increasing the heat under the chimney for efficient melting. Once the container reaches the required temperature, cans are added with the mouth facing up to avoid steam explosions. As the cans melt, impurities, slag, float to the surface, which are skimmed off using a stainless steel spoon. The molten aluminum is then poured into molds, such as an old muffin tin, to create ingots for future projects. Safety precautions are essential throughout. Sheet metal stamping is a crucial industrial process used extensively in the production of household goods such as aluminum cookware and refrigerator evaporator panels. It offers a cost-effective way to mass-produce precise, durable components with excellent mechanical properties. The materials commonly used are 3003 or 5052 aluminum alloys, prized for their corrosion resistance, thermal conductivity, and formability. The process begins with coil preparation, where large rolls of aluminum or stainless steel, thickness ranging from 0.6 mm to 2.5 mm, are fed into decoilers. A flattening machine relieves internal stress and ensures uniform thickness. The sheet is then passed through a hydraulic shear or press line to produce blanks. Round for cookware, diameter between 240 mm to 320 mm, and rectangular for evaporator panels. For aluminum cookware, the round blanks undergo deep drawing, a multi-stage process where the material is pressed into a cylindrical shape using dies and punches. Depending on the depth required, 2 to 5 drawing stages may be necessary. The cookware is then edge trimmed to remove excess material and ensure balance, followed by bottom flattening for stability on flat surfaces. Spinning or curling machines are used to finish the rim, while rivet or spot welding attaches handles made of stainless steel or heat-resistant plastics. Final surface treatments include anodizing, mirror polishing, or non-stick coatings like PTFE or ceramic. For refrigerator evaporator panels, 2 rectangular aluminum sheets are precisely stamped using matched dies to form refrigerant channels in zigzag or serpentine patterns. These are typically 0.8 mm thick and range from 300 mm to 600 mm in length. The 2 sheets are then aligned and fusion bonded, either through brazing, using flux and heating to around 600 to 620 degrees Celsius, or diffusion welding in a vacuum furnace. This creates a hermetically sealed structure capable of handling refrigerant pressure. The bonded panel is then trimmed, pressure tested, and coated with epoxy or powder paint for corrosion resistance. Both product types benefit from automated production lines, improving speed and consistency. For example, modern deep drawing presses can achieve cycle times of 8 to 15 seconds per piece, and robotic arms are often used for transferring workpieces between stations.